Okay, let's look at some examples from the 2.2 homework. And the first one I'm going to start with is number 2. So if you look closely at this question, it's asking for those 4 things that I talked about in the concept video that we can now determine purely based off derivatives. First off, relative extrema. Second, intervals of increasing or decreasing. Third, points of inflection. And fourth, intervals of concavity, or concave up or concave down. And so we're going to look at those 4 things with this function, and then using that, we'll sketch the graph. Okay, here's my function. It lists these things in a certain order, but we don't have to follow that order. We can do it in whatever order we want and then answer the questions at the end. And so that's what we're going to do here. Here's my function. First thing I'm going to look for is critical points. Where can my relative extrema happen? And to find those critical points, I'm going to find the derivative and set it equal to 0. So I get 12x cubed plus 16 times 3 is 48x squared. And then I'm going to set that equal to 0. Interesting, this one's a cubic function, so how do I solve something like this? I have to factor. But luckily, this one factors pretty nicely. Both terms have at least an x squared in it, plus 48 is divisible by 12. So that means I can actually pull out a 12x squared. What does that leave me with? That leaves me with an x in my first term and a 4 in my second term. And now I can just look at each factor individually. So where's that first factor equal to 0? That tells me that x equals 0 is the solution. And where's that second factor equal to 0? At -4. So those are my 2 critical points for this function. And they represent where I could possibly have relative minimums or relative maximums. How do we determine whether they're relative minimums or relative maximums? Well, I can either use the first derivative test or the second derivative test, but remember, we do need to come up with my intervals of increasing or decreasing, which is really what the first derivative test does anyway. So let's use the first derivative test because that'll also tell me my intervals of increasing or decreasing. That means I'm going to come over here and make a number line. What numbers do I put on that number line? I'm going to put both of my critical points, 0 and -4. Now what do? I'm going to pick numbers inside these 3 different intervals. Right? I have 3 intervals now that I'm working with. Everything after 0, everything in between -4 and 0, and everything before -4. So let me pick nice easy numbers. I'm going to pick 1, I'm going to pick -1, and I'll pick -5. If I'm using the first derivative test, I want to plug these numbers into the first derivative. So you'll notice with -5, I'm plugging -5 into my unfactored form of my derivative and seeing what I get there. And of course, I can just use a calculator to figure this out, and I get -300. Okay, remember what's important here? What's important here is the fact that it's negative. So the fact that that's negative tells me that my function is decreasing throughout this interval. Everything before -4, your function is decreasing. Now let's plug in -1 and look at this interval between -4 and 0. Well, I don't have to plug it into my original derivative. Remember, I factored this derivative, and if I plug it into this term, it might be a little more straightforward because I already have 2 different factors. When I plug -1, square it and multiply it by 12, this term ends up being positive. What about this term? -1 plus 4 is +3, so that term also ends up being positive. What happens when you multiply 2 positive values? You get something that's positive or something that's greater than 0. Remember, the actual value doesn't matter. I just care whether it's greater than or equal to 0. And so this is another way that you can use the first derivative test. You can keep your derivative factored and then just look at each of the factors of whether they're going to be positive or negative based off of what number you're plugging in. So this next interval, your derivative is positive, meaning your function is increasing. Last interval, everything after 0. Let me do something similar where I'm just going to plug in 1 into my factored form. And what do I notice about each term? This term's positive and this term's positive, meaning I have another interval where the derivative is positive. Now, if what I did with these last two derivatives doesn't make sense, feel free to just go about it the way we did it with the first one, where you just plug it into the derivative, use a calculator, get your number out, and then just check whether that's positive or negative. Okay, but that means that last derivative, or that last interval, my function is increasing. Perfect, so now we can go back to these critical points, and I can classify them as local minimums or local maximums, or relative minimums or relative maximums. So let's look at 0. What's happening at 0? My function is increasing, it flattens out at 0, and then goes right back to increasing. That means 0 is neither a relative minimum nor a relative maximum. Well, what about -4? -4, my function is decreasing, then flattening out, and then switching to increasing, meaning I have a relative minimum. Perfect. So I now have classified my critical points as relative minimums, relative maximums, or neither. Remember, that's always an option, is you could end up with a critical point that's not a relative minimum or a relative maximum. And I have my intervals of increasing or decreasing. So I can go ahead and say f of x is increasing over the interval -4 to 0 and 0 to infinity, and the function is decreasing over the interval -infinity to -4. Okay, and that takes care of those first 2 points that require the first derivative. I have my relative extrema, and I have my intervals of increasing or decreasing. To move on, to look at points of inflection or concavity, I need the second derivative. So let's go ahead and find the second derivative here. When I take this derivative, I get 36x squared plus 96x. What do I do with the second derivative? Well, if I want to know my intervals of concavity, I need to know the possible places where that concavity can switch, which means I need to know my inflection points. And how do I find the inflection points? The same way I found my critical points, by setting this second derivative equal to 0 and solving. Well, this is another example where I can just factor. I can factor to solve this. So I can actually factor out 12x. That leaves me with 3x with the first term and just an 8 with the second term. And now I can focus on each different factor, and that tells me that x equals 0 and -8/3 is the solution. Now, careful, this is an easy mistake to make. I'm not going to classify these as inflection points yet. All that we can say are these are my possible inflection points. Remember, the definition of an inflection point is if the concavity changes. So we first have to check that the concavity changes. How are we going to do that? Check my intervals by making a number line. But this time, what am I going to put on my number line? I'm going to put my possible inflection points. So 0 and -8/3. And now I'm going to do the same exact thing I did with the first derivative test, where I'm going to pick numbers inside each of these intervals. So I'm going to pick 1 again. I'm going to pick -1 again, because that's in between 0 and -8/3. And then with this one, I'm going to pick -3. -3 is -9/3, which is more negative than -8/3. But now I'm checking the second derivative. So I'm going to be plugging these values into my second derivative. And once again, I'm going to use my factored form because I like doing it that way. So I get 12 times -3 times -3 plus 8. 12 is positive, -3 is negative. 3 times -3 gives me -9. -9 plus 8 is negative. So what do I get? Positive times a negative ends up giving you a positive value. So this first interval, your second derivative is positive. What does that mean again? That means I have upwards curvature. Okay, what about a -1? I have 12 times -1 times 3 times -1 plus 8. This term is positive. This term is negative. 3 times -1 is -3. -3 plus 8 gives me a positive value. So now I have a positive times a negative times a positive, which overall is a negative number. So this next interval, in between -8/3 and 0, I'm concave down, or I have negative curvature, downwards curvature. Last interval, I get 12 times 1 times 3 times 1 plus 8. And in this case, all of my factors are positive, and so therefore the second derivative here is positive. Meaning again, I have upwards curvature. These possible inflection points of 0 and negative 8/3, does the concavity change at those points? I go from positive to negative and then from negative to positive. So yes, the concavity changes. Therefore, these are inflection points. 0 and negative 8/3 are both inflection points because the concavity for sure changes. And because we've already tested whether the concavity changes, I can now declare that f of x is concave up over the interval negative infinity to negative 8/3 and the interval 0 to infinity. And the function is concave down over that interval of negative 8/3 to 0. Perfect. So now we were able to answer all four of those things. We found the relative extrema, we found the intervals of increasing or decreasing, we found the inflection points, and we found the intervals of concavity. So the only other thing we have to do now is we have to sketch the graph. Well, for this graph, all I'm looking for is a function with a relative minimum at -4 and a spot at 0 where it flattens out but is neither a relative minimum or a relative maximum. And if you double check this with your second derivative, notice how from here to some point in between -4 and 0, which we know now to be negative 8/3, I'm concave up. And then right here, I switch to being concave down because I have an inflection point there at negative 8/3. And then what happens at 0? I switch back to being concave up because I have another inflection point at 0. Okay, the next one we're going to look at is number 5. And I chose this one because this one's very related to the second derivative test. Using the second derivative to determine whether we're working with a local minimum, or a relative minimum, or a relative maximum. So this one just gives us a bunch of information about the derivatives, and then it wants us to sketch the graph. So in some ways, a lot of the work's already done for us. But what I want to do here is I want to analyze what each piece of this information is telling us. First, it tells me that the derivative at 5 is equal to 0, right? F prime of 5 is equal to 0. So the derivative at 5 is equal to 0. What does that tell me? That tells me that 5 is a critical point. And that's all it tells me so far. If the derivative is 0, that means that I have a critical point at that x value. So let's keep going. Next, it tells me that the second derivative is negative at that same x value. So what does that mean? That means I'm concave down. And at this point, using the second derivative test, what does that tell me? Based off the second derivative test, this tells me that x equals 5 is a relative maximum. Just based off of those two pieces of information. So I know there's a relative maximum at x equals 5. If I keep going and I look at this piece of information, what does that tell me? F of 5 equals 4, all that tells me is where that y value actually is. So I have a relative maximum there, and that maximum reaches a height of 4. Okay, let's keep going. And this is going to look pretty similar. F prime of 1 is equal to 0. What does that tell me? I have a critical point at 1. Keep going. The second derivative, in this case, is positive, meaning I'm concave up. So with this second critical point, I'm concave up. Therefore, by the second derivative test, x equals 1 is a relative minimum because I have a critical point where the second derivative is negative. What does this tell me? Just the y value. That's all that tells me, is just how low does it actually go. It goes down to -2. And honestly, at this point, now that we know both of these relative extrema, I can actually go ahead and answer this question. Take a look at these graphs. Which graphs can we go ahead and eliminate? I can eliminate C and D because they only have one relative extrema. C only has a relative minimum. There is no relative maximum. D only has a relative maximum. It doesn't have a relative minimum. And this graph should have both. So let's look at A and B. Which one has a minimum at 1 and a maximum at 5? That's B. B has a minimum at 1 and a maximum at 5. And I'm talking about the x values at x equals 1 and a maximum at x equals 5. So we've already answered the question, but let's look at just what this last piece of information tells me. F double prime of 3 equals 0. So what's happening at 3? At 3, we have an inflection point. And once again, this piece of information just tells me what the y value is there. And if we zoom in here, we can actually see that's true. So here's x equals 3, and previous to that, I'm concave up, and after that, I'm concave down. So it's that point where the curvature changes. And that's all there is to number 5. So good luck with the rest of the homework, and reach out if you have any other questions.